realize this displacement. This is actually in your mind. This is a mathematical problem. And what does this problem? Is that just like a test or prompts a voltage, this prompts a force. So if there is a force and if there is a virtual displacement for the system, then if the work done is zero, it says that the numerical value of the force is zero. In other words, the system is in equilibrium. You can say the reverse also. If a system is in equilibrium, which means the forces are zero, then the virtual work done by this force is zero. So in a way, this is a restatement of what we call as the equilibrium. When a system is in equilibrium, the total forces is zero. This is another way of saying it, maybe an operative way of saying it, because what does a force do? It does work. So we say that when it does not do any virtual work, the force is zero. It's a mathematical statement for saying that force is equal to zero. Clear? And why we always use virtual? Because we ensure that the work done is zero, not due to any peculiarity of the evolution of the system. Clear? So virtual displacement is such a displacement which is non-zero if force is non-zero. Then the principle of virtual work. And remember, the statement of principle work is something that you should keep in your mind, because that is something which every student or most of the students go wrong when they write in the examination. It's a statement of the condition for equilibrium. What does it say? It says that if a system is in equilibrium, then the virtual work done by the applied forces is zero. And again, when we discuss Newtonian formulation, there was nothing about constraints, because constraints are due to discontinuous forces, and Newtonian mechanics is for continuous forces. So when we do this classical mechanics, means our course, there could be constraint forces as well. So in the definition of virtual work, we also say that this displacement is consistent with the constraints involved in the system, or the constraints of the system. So we can say that the principle of virtual work is for applied forces, not for the forces of constraints. Then an extension of what is called the principle of virtual work is only for those dynamical systems which are in equilibrium. But you know that we are more interested in systems which are not in equilibrium, isn't it? We are more interested in doing mechanics of systems which are evolving. So we can extend the principle of virtual work to all the systems, all dynamical systems, and that is what we call as the D'Alembert's principle. And D'Alembert's principle states that for any system, any dynamical system, the sum of applied forces and the reverse effective force does no virtual work. So that is actually a definition of the D'Alembert's principle. And in the last class we said that D'Alembert's principle is the single most general statement in classical mechanics, or that is the starting point of classical mechanics. That is even more fundamental than the Newton's equations, because for reaching D'Alembert's principle starting from Newton's equation, we have to assume that it is valid also for the force of constraints, which are discontinuous forces, because Newtonian mechanics deals only with continuous forces, because constraint forces act only at certain points. It is not a continuous force. If you think about gravity, it is everywhere. It means if a particle is moving under the action of gravity, that gravitational force or that potential is at all the points it is there. But what about the constraint force? Suppose I throw a stone, it cannot go beyond the wall. That is a constraint. But that force of constraint acts only at the point of contact, not before that, not after that. That kind of forces are not included in the discussion of Newtonian mechanics. Clear? So reaching D'Alembert's principle starting from Newtonian formulation requires certain assumptions, but the reverse doesn't require. In that way, D'Alembert's principle is more general than even Newton's equation of motion. Now, we can obtain the equations which we were searching for, that is Lagrange's equations starting from D Alembert principle, that is Lagrange's equations. See, if you go through your lecture notes, you will see that the title was given as Lagrangian mechanics, the description of motion in configuration space. So, analogous to that, if you think about Newtonian mechanics, it is the description of motion in Euclidean space using what kind of coordinates? Cartesian coordinates. So, there are three things: Newtonian formulation, Euclidean space, Cartesian coordinates. You can say that the Euclidean space is spanned by the Cartesian coordinates. Now, if you come to Lagrangian formulation, we have the Lagrangian formulation, then configuration space, and generalized coordinates. And there is nothing like generalized coordinate system, generalized coordinates. And about generalized coordinates, we have maybe discussed at length in previous classes. Now, in Newtonian formulation, if you go back to Newtonian formulation, you will note that there is an equation of motion, which is the second law of Newton. What does it tell us? Or what is the use of it? What is the role of it in Newtonian formulation? It gives us an equation, and if you solve that equation, which is a differential equation, you get the trajectory of the particle. Isn't it? You get the trajectory. You can do the calculations forward or backward. It tells us how R changes with time. What is Newton's equation? It is F is equal to m a. So it is F is equal to m d square r by dt square. You can replace f by its analytical form depending on the situation. You can write an analytical form for f. This form for f will include parameters such as mass or charge. Then it will contain r or r dot, isn't it? And never anything more than a. So we say that this is a second order differential equation. So if you solve this, our answer is r as a function of t, which means the trajectory of the particle as a function of time. And if you have this expression, then you can find its position or the state at any instant, forward or backward. We can do the calculation. That is the role of our equation of motion in Newtonian formulation. Similarly, in Lagrangian formulation, when we describe the evolution of a system in configuration space using generalized coordinates, we need an equation or a set of equations. Those equations are called Lagrange's equations. Here also, in fact, this is one vector equation which can be broken down into three scalar equations. So it tells us what is the x, y, and z as a function of time, isn't it? Now the same thing is applicable in Lagrange's equation also. This equation should give us the answer for the values of qj at any instant of time t. So if we solve the equation which we are searching for, what we will get is the trajectory in configuration space. What will be the answer? Answer will be what is the value of each and every generalized coordinate at any instant of time t. This is called the trajectory. Like r as a function of t is the trajectory in Euclidean space using Cartesian coordinates. And here qj as a function of t gives us the trajectory in configuration space using generalized coordinates. So our equation should be a differential equation, solving which we should get qj as a function of t. Now here we have one vector equation of three scalar equations, three equivalent scalar equations. So for a system with n degrees of freedom, we will have n qj's. So how many equations should be there? N equations should be there, one for each qj. They will have the same form. They have the same form. And just like here, x, y, z, all three equations have the same form. Just like that, we have an equation for each qj. So if n degrees of freedom are there, n equations will be there. each equation tells us how each generalized coordinate change as a function of time. And when we solve this differential equation, we have a trajectory. It may not be the real trajectory. Sometimes it may be the real trajectory, but that is the trajectory in configuration space. Now, what we are going to do is a purely mathematical thing, starting from Lagrange principle. We will reach the equations which you all know, or the set of equations which you all know. That is the first part. Probably we will finish up to that today. Then what we will do is we have to do all the problems given in textbooks, at least the examples which are given, and possibly the other means those workout means the questions also, to familiarize yourself with the solution of Lagrange's equations, the use of Lagrange's equations. And remember that you know those equations. Most often, the problem is not in solving the equation, but in choosing the generalized coordinates. How you obtain, how you choose the generalized coordinates. That is what is tested in a problem. The solution may be purely mathematical thing, but the judicious choice of generalized coordinates in each case needs some physical insight also. What you have to choose. For example, if it is simple pendulum, you have two choices. One is x and y, second one is r and theta. Which one will you choose? Why you choose r and theta? Why? They are independent of one another. So whether the length of the pendulum is constant or not, r and theta is preferred over x and y. Clear? Because x and y, they are depending on one another. They are not mutually exclusive. X square plus y square equal to the length square. So when you use r and theta, they are generalized coordinates. They are the proper set of generalized coordinates. So like that, in each problem, choosing the generalized coordinates itself becomes our contribution, rather than just solving it. Of course, solving it is also important when you come to your examination, but the first point is the choice of the generalized coordinates. Now, let us obtain the Lagrange's equations of motion starting from Lagrange's principle. What we will do is, you may also write the important steps here, because this is possibly one of the essays for your examination. So you consider a system of particles with n degrees of freedom. Small n degrees of freedom. Let the system be described by the generalized coordinates qj. When you write qj, you should write j goes from 1 to n. Now, the transformation from the I be the Cartesian coordinates for the ith particle, then the transformation from I to qj is given by the set of equations I equal to equations that connect the Cartesian coordinates for the ith particle and the generalized coordinates. You can write the reverse equation also. So this is not a single equation actually. If there are capital N particles, then capital N equations of this form are there. Let this be equation 1. Now, VI means the time derivative of R or R and dot. Can be written as sigma I rho Ri by rho Qj dot plus rho Ri by rho P. Remember, just like equation 1, equation 2 is also a set of equations for each I. If there are capital N particles, capital N equations are there for both equation 1 and equation 2. So our objective is to start from the D'Alembert's principle and end with Lagrange's equations. So these are certain preambles which we require for those mathematical steps. And again, the arbitrary virtual displacement delta I can be written as delta I equal to sigma j rho Ri by rho Qj delta Qj. Delta I is the virtual displacement in Cartesian coordinates for the ith particle, and delta Qj's are the virtual displacement in generalized coordinates. Now if you look at equation 3, again you have capital N equations if it is a system with N particles, and for each equation on the RHS how many terms are there? If small n degrees of freedom are there, then that many terms are there. Here. So when you look into those equations, you should always check whether, in your mind, you should check whether it is a single equation or a set of equations. Here, when you do sigma j, it is understood that j goes from 1 to n. Now the D'Alembert's principle states that sigma I minus Pi dot delta I equal to 0. Mention 4. Here Fi is the force on the system and minus Pi dot is the reverse effective force. Actually Fi is the force on the ith particle and minus Pi dot is the reverse effective force on the ith particle. So what we will do is, this will be one of our landmarks, or starting point actually, the D'Alembert's principle in this mathematical form. And now what we have actually a number of terms on the LHS and RHS is 0. See, we can divide these terms into Fi dot delta I terms and minus Pi dot delta I terms. We will rearrange, or what we will do is we will replace delta I, or we will write delta I in terms of delta Qj's, then we will do some rearrangement and all, and then finally get our equation. So you can just go through what we have written till now and ask any doubt or clarification required. No. Okay, madam. So what we will do is, the next step is this one. The next step is, now the first term on equation 4, on the LHS of equation 4 is sigma I Fi dot delta I. Then you written as sigma I Fi sigma j rho I by rho Qj delta before, maybe in some previous class, maybe by defining generalized force. So we will do the same here. This can be written as sigma j qj delta qj equation 5 sigma I fi dot delta I, where qj equal to sigma I fi dot ri by dot qj. So here what we have done is we have interchanged the order of summation. J comes first and I goes inside. Then this many terms we club together and replace by the symbol qj. And qj is called the generalized force. Now, as we said, qj, small qj's, generalized coordinates need not have the dimension of displacement. They need not even be geometrical quantities. So qj's need not have the dimension of force. But qj into delta qj always has the dimension of work. That is ensured. So it is something like we have a control still over the dimensions. We have the freedom to use any quantity as the displacement, but still we have the control because the generalized force is defined in such a way that generalized force multiplied by displacement, generalized displacement still have the dimension of work. So here capital qj's are called the components of generalized force. Components of generalized force. So you can write that here small qj's need not have the dimension of length. Do not have the dimension of length, and hence capital qj's need not have the dimension of force. But qj dot delta qj or qj delta qj has the dimension of work. See, this statement, you all said this statement, even before I said it, you all said that it's a dimension of work. But you just think about it. For example, in the case of a simple pendulum, if you are using r and theta as generalized coordinate, one component has one dimension, the other component has another dimension, isn't it? Because Q1 and Q2, Q1 is R, Q2 is theta. So capital Q1 will have a dimension such that capital Q1 into delta R has the dimension of work. The other component Q2, capital Q2 has the dimension such that Q2 into delta theta has the dimension of work. So the freedom which this kind of generalized coordinate gives us is immense actually. But still we have a control, because the product has the dimension of work. It's a very clever way of doing mathematics. So this is again another landmark of our derivation. This was the first landmark and we have taken the first term. Now naturally what we have to do is we have to take the second term. And there the rearrangement is slightly more, and then we will get our equation. So the second term on the LHS of equation 4 is sigma I Pi delta Ri equal to sigma I Mi. See, Pi is mass into velocity or Mi into Ri dot. So Pi dot, there will be two dots. And we are discussing systems where the mass is not changing with time. So you can put M as M itself. And Again, delta Ri can be written in terms of the virtual displacement in generalized coordinates delta QGs. Here also what we do is we change the order of summation. Sigma j is taken out, sigma I, then I double dot, rho I, the j, delta, and LHS is sigma I, Pi dot delta R. Now, what we do is, we have this term inside. This is Mi Ri double dot dou Ri by dou Qj. Of course, the summation is also there. Now, this term can be written as two terms using the expansion d by dt of A into D is dA by dt into D plus A into dB by dt. We say this is one of the terms because this term can be written as d by dt of Mi Ri dot. So this can be expanded like this. I will start from, maybe more space is required. So I will start from here, sigma j, sigma I, d by dt of Mi Ri dot dou Ri by dou Qj minus sigma I, Mi Ri dot d by dt of dou Ri by dou Qj, delta Qj is, and LHS is sigma I, Pi dot delta R. See, this is d by dt of A into D minus A into d by dt of B, which gives us d by dt of A into B. Why we write it like this? Because we are searching for an equation. This is another landmark of our derivation because here we have to do some more manipulation of the terms. Now, d by dt of dou Ri by dou Qj this term d by dt of dou Ri by dou Qj. We know that there is nothing happens if we reverse the order of differentiation. So dou by dou Qj of dou Ri by dou Qj. So dou Ri by dou T is Ri dot, which we can put as Pi. So this is equivalent to dou by dou Qj of Pi. So d by dt of dou Ri by dou Qj is same as dou by dou Qj of Pi. dou Ri by dou Qj dot plus dou Ri by dou Ri by dou T is same as V is equal to sigma I dou Ri by dou Qj dot plus dou Ri by here this is small a and then this is small b. Here we have expressed the dri by dt, that is di, in terms of Qj. Okay, if you look at the equations A and B, have you written till have you reached this point B? Now if you look at the equation A and B, you can note that d by dt of dou Ri by dou Qj, this term, is equivalent to dou Vi by dou Qj. Now Vi is actually this one. Va is this one. So from these two, d by dt of dou Ri by dou Qj is same as dou Vi by dou Qj from these two, dou Vi by dou Qj dot, that is equal to dou Ri by dou Qj. Dou Vi by dou Qj dot. What is the coefficient of Qj dot in this expression? Dou Ri by dou Qj. Let this be equation C. So we can use equations A and C and write sigma I Vi delta Ri equal to sigma J sigma I d by dt of Mi dou Ri by dou Qj minus sigma I Mi Ri dot. Instead of d by dt of dou Ri by dou Qj, we can write dou Vi by dou Qj. This term d by dt of dou Ri by dou Qj, this can be replaced by dou Vi by dou Qj. Dou Vi by dou Qj into delta. Now dou Ri by dou Qj, this term, we can replace dou Ri by dou Qj by dou Vi by dou Qj dot. So this is it. Sigma J sigma I d by dt of Mi Ri dot dou Vi by dou Qj dot. Va is Ri dot actually. Minus sigma I Mi Ri dot dou Vi by dou Qj delta Qj. Put it here. Now Ri dot can be replaced by Vi and this also by Vi. So this is sigma J sigma I d by dt of you write it as half the dou by dou qj dot of half mi bi square. If you take a derivative with respect to qj dot, what you will get? Half that mi 2 bi dou bi by dou qj dot. Okay. So what we are doing is we are introducing the kinetic energy term. Here is bi square, which means the kinetic energy in terms of the kinetic energy we will calculate it using Cartesian coordinates or generalized coordinates. The value remains the same. So it is half mi bi square minus dou by dou qj of sigma I half mi bi square delta q. Remember, the summation and delta q is always there. So this is not a single term. You have small n terms like the term inside the bracket. That's very important. So this is equal to sigma j d by dt dou t by dou qj dot minus dou t by dou qj delta qj. LHS is sigma I bi dot delta r. Let this be equation 6. Here T is the total kinetic energy of the system. Now, this is another important landmark in our derivation. So we started from the equations that connect Ri and Qj. We wrote the expression for Vi, the expression for the virtual displacement in Cartesian coordinates in terms of the virtual displacement in generalized coordinates. Wrote down the mathematical statement of the Lagrange principle, took the first term and actually transformed the term in terms of generalized force and generalized the coordinates. Took the second term. Here the manipulation is more actually. So what we have done is we have used the equation d by dt of ab equal to dA by dt into b plus a into dB by dt. Again, we did some manipulations and obtained an expression for PA delta Ri in terms of the kinetic energy, generalized the velocity, and generalized the coordinates. Now, 6 and 5 can be put back in equation 4. So, using equations 5 and 6, in equation 4, we get sigma j qj delta qj minus sigma j d by dt dou t by dou qj. Qj dot is called the generalized velocity. Capital Qj is the generalized force. Capital T is the kinetic energy. See now, let this be equation 7. Now comes the most important step of this derivation, which most people does not like for the examination. See, when we evaluate the answer sheets, this step will invariably carry one of the rules, because the next step, how do you remember the next step? What we will say is each quantity inside is 0. But how we can say that? We can say that because generalized coordinates are independent of 1. They are independent of one another. So, if you look into this equation, how many terms are there from the LHS? When we say term, what we mean is the quantity inside the square bracket. If there are small n degrees of freedom, there are small n qj's, small n generalized coordinates. In that case, small n terms are there. because you can put 1 q1 d by dt of dou t by dou q1 dot plus dou t by dou q1 delta q1 plus similar term with 2, similar term with 3, so on up to small n. So this many terms are there. When we say term, what we mean is the quantity inside the square bracket. So and RHS is 0. So this is ensured for any virtual displacement for the set delta qj. For any combination delta q1, delta q2, delta q3, this is ensured. And delta q's are independent of one another, which means the change in one coordinate is not cancelled by change in another coordinate. Just like our xy is. Suppose you change x by 1 unit, you cannot cancel that movement by changing y or z. Isn't it? If you move one point, suppose we have a point power, it is at the origin. This initially moved along the x-axis through 1 unit. Whatever you do, whatever movement you do in y or z coordinates will not negate this change. If it has to go back to 0, what you have to do? You have to move it through y only. That is because y is orthogonal to x and y. Similar is for y and z. They are mutually exclusive. They can be changed arbitrarily. You can move from 0 to plus infinity without changing y or z. And even if you move 1 unit, for negating that change, you have to do the reverse. Any change in y or z will not affect the movement along x. The same is true for generalized coordinates. Clear? That is the difference when you use r and x and y for a simple pendulum and r and theta. R and theta are independent of one another. So, since generalized coordinates are independent of one another, for this equation to hold, for any set of delta qj's, each quantity inside the bracket should be 0. It is q1 considered that this quantity should be 0, q2 should be 0, all these things should be 0. So the quantity inside the bracket should be, so how many equations we will get? If there are small n degrees of freedom, small n equations we will get. So as the generalized coordinates qj's are independent of each other, delta qj's are also independent. So have you got the idea? You just have to think about x, y and z. See, we can do that because x, y, z are orthogonal to one another and can be used as a generalized coordinate in the case of the particle which we were discussing. But if it was the problem was for a simple pendulum, you cannot have that because x and y are the Lagrange. Hence, delta qj's are also independent. So, for equation 7 to hold, for all values of delta qj's, the term inside the bracket should be 0. The term inside the bracket should be 0. That is maybe we no more need the bracket. How many equations are there? You have n equations of this kind, j equal to 1 to n. Because we started with small degrees of freedom. Or maybe we can write in a better form, d by dt of dou t by dou qj dot minus dou t by dou qj equal to capital Qj, j equal to 1 to n. How many equations are out there? Small n equations are of this form are there. If degrees of freedom is small. Actually, these are the Lagrange equations of motion. So what we have done is we have started from D'Alembert's principle, then obtained n equations. Now what is the old way by these equations? If you solve these equations, you could obtain the trajectory in configuration. But do you agree with me? These are the Lagrange equations what you have learned earlier? No. You have learned the Lagrange equations in terms of a function L. L was defined as T minus B. Both T and B expressed in terms of the generalized coordinates. So we will reach that equation later, but this is the Lagrange equation. The most general form of Lagrange equation is this one. Maybe from our first class itself, we were always saying that general things are better, isn't it? So this is the general form of Lagrange equation because this is applicable for all systems. The form which is familiar to you is true only for conservative systems. In the case of conservative systems, we can do some more modification and obtain the equation which you have already learned. But this is the general form of Lagrange equation. By general, this meant that this form of the equation is true for all the systems, whether it is conservative or non-conservative. Whatever be the type of constraints present, this is the general form of Lagrange equation. And for a system with smaller degrees of freedom, this is actually not a single equation. This is a set of equations, one corresponding to each generalized coordinate. Now here Qj is generalized force, T is kinetic energy, Qj is generalized coordinate, T is time, and Qj dot is generalized velocity. Now let us see how we can reach the more familiar equation which is true in the case of conservative systems. Of course, you have to write up to that and only then the derivation is complete. So, now if all the forces are conservative, then the potential V is a function of only coordinates. Then the force Fi is given by negative gradient of Vi. See, but we have put it as negative gradient of Vi. We have given a subscript I here. It shows that this del is for the ith particle. Clear? Because we are discussing a system where there is more than one particle. For each particle, you have to have xy, z. And this V is not the velocity, we shall put it as capital V, that is the potential. For Fi equal to minus rho Vi by rho r. Now, the generalized force Qj is sigma I Fi rho ri by rho Qj. See, you always remember this one, isn't it? Negative gradient of potential. Now, what will happen if we put it as positive? How much wrong it will be? You are actually saying that maybe all the waterfalls they are flowing from down to up. That's what difference will be there if you somehow forget to put negative sign. See, the whole thing will be different. The entire thing will be upside down. So it's not just the gradient, it's defined as the negative. So here we will substitute for Fi, then it is rho Vi by rho ri, rho ri by rho J. We can note that this will be rho V by rho Qj. Where capital V equal to summation of all the potentials. Qj is negative gradient with respect to Qj of the potential V. And you can have such a potential which is a function of coordinates only for systems which are conservative. And how we have to write down Lagrange's equation for non-conservative systems, we shall see in a later section. We can extend that to non-conservative systems also. So I think it's clear up to this point. So we can substitute for Qj in equation 8 from this, maybe let this be equation 9. Substituting for Qj in equation 8 from equation 9, we have d by dt of rho t by rho Qj dot minus rho t by rho Qj equal to minus rho v by rho Qj. And remember always to put j equal to 1 to n. This tells that this is not a single equation, there are n such equations. Now, this V depends only on coordinates. For a system which is conservative, the potential will not depend upon Qj. No, it will depend only on Qj's. So what we can do is, if we can rearrange the terms and write it like this: rho t by rho Qj dot minus since V does not depend on Qj dots, we can put T minus V here also. In that case, it becomes d by dt of rho T minus V rho Qj dot minus rho T minus V by rho Qj equal to 0. This will not alter the result because V, for a conservative system, V does not depend on Qj dot. This is just for our convenience. Now we have something like T minus V on both the terms. Now we introduce a function. That function is called a Lagrangian of the system. Now we define a function Lagrangian as T minus V. Then this equation becomes d by dt of rho L by rho Qj dot minus rho L by rho Qj equal to 0. Remember, put j equal to 1 to n. Equation 10. This set of equations are called the Lagrange's equations for the conservative system. So, what is the whole played by this equation? The whole played by this equation is same whole played by Newton's equations in Lagrange formulation. If you solve this equation, you can have Qj's as a function of time. Clear? See, you think, you can note that what should Qj depend on? Qj should depend upon the energy and the mass. Correct? Which means it should depend upon the kinetic and potential energies. All these things are here. But the form is not, the point is this is a first order differential equation. This is a first order differential equation. Newton's equation was a second order differential equation. The solution of that required two integrations, which means 6 initial values are required. Here, only one integration is required for solution. Now, the solution of this equation should give us L as a function of Q and time, from which we could get an expression for Q as a function of time. So, this equation describes the evolution of the system in configuration space, just like Newton's equations tells us the evolution of the system in Euclidean space. These are the Lagrange equations. This is the general form which is true for any system, and this is the form for a conservative system, because most often we deal with the conservative systems. Now you have a number of assignments. What you do is you go through those problems. We shall discuss them in the class also. First is the Lagrange equations of motion for a one-dimensional harmonic oscillator. A simple pendulum. A double pendulum. Triple pendulum, for a projectile, and all the examples in your textbook. Try to go through all the examples, and as I said, give importance not only for solving that differential equation. The way you obtain the equations itself is the most important. In many cases, like triple pendulum, you need not solve those equations. You obtain those equations. How to obtain those equations? You have to express T and V in terms of the generalized coordinates of the problem. Then you write down these equations. For example, if it is a simple pendulum, obtain the expression for T and V in terms of R and theta. Then for R you write one equation, for theta you write another. If you solve those equations, you will get how R and theta changes here. And when you go through the problems, we will understand more about it. Maybe that we will do in the next class, or when we discuss problems after going through. Now, this is the equations which we were searching for. So, go through this derivation. Actually, this is the simplest derivation for your paper. So, you must learn. And again, next day what we will do is that we will start from another point. Here we have started from the D'Alembert principle and obtained these equations. The general form was obtained, and also for the conservative system. This is the equation which you know. And remember, this is not a single equation, it's a set of equations. This is a first order differential equation. Now we will reach the same equation again using the concept of calculus of deviations. That we will discuss in the next class. And if you could understood this well, means you can go through this number of times and be thorough with it, then the other thing will be very easy, and you can do the problems also without much difficulty and ambiguity. Okay. So, you പഠിക്കുന്ന കാര്യം മനസ്സിലാവുന്നുണ്ടോ? മനസ്സിലാവുന്ന പറഞ്ഞാൽ ഏത് ഇക്വലിറ്റി കാര്യമില്ല. You have to introduce that in your examination. So, അതിനെ നമുക്ക് ഈ അവസാന നിമിഷം വരെ വെച്ചുകൊണ്ടിരുന്നാൽ നടക്കില്ല. സ്റ്റാർട്ട് നമ്മളിപ്പോൾ പഠിച്ച് പോകുന്ന ആ വീക്കിലെങ്കിലും അത് മുന്നോട്ട് പോകണം. കാരണം എല്ലാവരും ഒന്നിച്ചെങ്കിലും പറ്റും. You have only one day before each examination. എപ്പോഴും അങ്ങനെ. You have only one day before each examination. അതുകൊണ്ട് ഇപ്പോഴേ നമ്മൾ എക്സാമിന് വേണ്ടി സ്റ്റാർട്ട് ചെയ്താൽ മാത്രമേ ജനുവരി അവസാനമെങ്കിലും എക്സാം കാണാം. സോ ഇപ്പോഴേ അതിനുവേണ്ടി ശരിക്കും പഠിക്കുക. ഈ റിസർവേഷൻ ഒക്കെ what you have to do is you have to write it a number of times. Maybe first time you have to give it your long time, right? Sometimes when you do it without doing it without, you may stop at some point. Then you can again after. You have to do like that. Only then you can do that. And maybe you can have an outline for each essay, like some landmarks. Either essay you can have 4 landmarks. This is one point, and that point can be between, even if you found it, you can reach. That is the only way you can do with such long essays. Clear? That's in the part.